Planck's law, the revolution that birthed quantum physics. What is Planck's law? Planck's law describes how much electromagnetic radiation is emitted by a perfect blackbody at different frequencies and temperatures. At its core, it reveals that energy isn't continuous like we experience in everyday life, but comes in discrete packets called quanta. The law can be mathematically expressed as shown in the screen, where B is the spectral radiance, H is Planck's constant, which is 6.626 times 10 to the negative 34th joule times second. Nu is frequency in hertz. C is the speed of light in meters per second. K is the Boltzmann constant, and its exact value is 1.380649 times 10 to the negative 23rd joule per Kelvin. And T is temperature in Kelvin units. The crisis that sparked a revolution. To understand why Planck's law was revolutionary, we need to travel back to 1900, when classical physics faced its greatest crisis. Scientists were studying blackbody radiation, the light emitted by objects when heated. Think of how a piece of metal glows red hot, then white hot as you increase its temperature. Classical physics predicted something called the ultraviolet catastrophe. According to the established Rayleigh-Jeans law, as wavelengths got shorter, moving toward ultraviolet light, the intensity should increase without limit, reaching infinity. This meant that any heated object should emit infinite energy, clearly impossible in the real world. Experimentally, however, scientists observed that blackbody radiation had a characteristic curve. Intensity would rise to a peak and then fall off at shorter wavelengths. Reality didn't match theory, and physics was in crisis. Planck's radical solution. Max Planck, initially trying to save classical physics, made a desperate mathematical assumption that would change science forever. He proposed that electromagnetic oscillators in heated materials could only emit or absorb energy in discrete chunks, not continuously. This led to his famous equation, E equals H, later names Planck's constant, times nu. This simple formula states that the energy of electromagnetic radiation is directly proportional to its frequency. The constant H, now called Planck's constant, serves as nature's fundamental quantum of action. What this means in practice. Planck's discovery revealed that energy is quantized. Just as matter comes in discrete atoms rather than a smooth continuum, energy comes in discrete packets called photons. Imagine climbing stairs versus walking up a ramp. On a ramp, you can stop at any height. Energy is continuous. On stairs, you can only stand on specific steps. Energy is quantized. In the quantum world, energy behaves like stairs, not ramps. When an atom emits light, it doesn't gradually release energy like water from a faucet. Instead, it releases specific amounts of energy all at once, like dropping coins from your pocket. Each coin is a photon with energy determined by Planck's equation. The birth of quantum theory. Although Planck initially viewed his quantization as merely a mathematical artifice, other physicists, like Einstein, recognized its profound implications. Einstein used Planck's concept to explain the photoelectric effect, showing that light itself consists of particle-like photons. This particle-wave duality became a cornerstone of quantum mechanics. Light behaves as both a continuous wave, showing interference patterns, and discrete particles, photons, that can be counted individually. Why Planck's law matters today. Planck's law successfully explains the blackbody radiation curves that classical physics couldn't. It tells us why the sun appears yellow-white. Its peak emission occurs in the visible spectrum due to its 5800 K surface temperature, and why infrared cameras can detect heat signatures. More fundamentally, Planck's work launched the quantum revolution that underlies all modern technology, from computer chips to medical imaging, from solar cells to quantum computers. Every time you use a smartphone, you're relying on quantum effects that trace back to Planck's 1900 insight. The quantization of energy revealed that our everyday experience of smooth, continuous change masks an underlying reality of discrete jumps and probabilistic behavior. In the quantum realm, nature doesn't make gradual transitions. It leaps from one allowed state to another, carrying exact amounts of energy determined by Planck's constant. This discovery represents one of the most profound shifts in human understanding since Newton, revealing that reality at its most fundamental level operates by rules completely different from our everyday intuition.
Thanks for listening to the Wonders of Science channel, where curiosity meets discovery. Stay tuned for more fascinating insights into the mysteries of our world. Keep exploring, and until next time, never stop wondering.